That is how long it takes a single radio signal traveling at the speed of light to cross the empty distance between a spacecraft launched in 1977 and the small room in Southern California where a handful of engineers are still waiting for it to make sense. On this particular day, they were not expecting words. They had stopped expecting words months earlier. What the spacecraft had been sending back, day after day, was a steady stream of numbers with no meaning attached to them. Technically a signal, technically data, and completely unreadable. Like a phone that still rings but only plays static when you finally pick it up. Then, buried inside that static, something changed. One section of the signal did not match the rest of it. It had a shape, a rhythm. Faint, but distinct from the noise surrounding it. An engineer with NASA's Deep Space Network noticed the anomaly first. He pulled out an old printed reference, the kind built decades earlier for decoding a spacecraft's raw memory by hand, and began comparing what he was seeing line by line against what should have been there. It was not gibberish, it was code, and it was about to explain everything. This is the real story of Voyager 1 STIS, the machine that went silent 15 billion miles from home, and the improbable message that brought it back. On November 14, 2023, engineers at NASA's Jet Propulsion Laboratory in Pasadena, California first noticed the problem. Voyager 1's radio signal was as strong and steady as it had ever been. The carrier wave never dropped. But the information riding inside it had stopped making sense. It wasn't a weak signal. It wasn't dropped data. It was a spacecraft, speaking fluently in a language that had, seemingly overnight, stopped meaning anything at all. Nothing about Voyager 1's trajectory had changed, nothing about its speed. As far as anyone on Earth could tell, the probe was exactly where it should be, still pushing outward through interstellar space at more than 38,000 miles an hour. It simply could no longer describe what it was doing or seeing to anyone listening. For a spacecraft that had already outlived its original mission by roughly 9 times over, that kind of silence carried real weight. Mission controllers had a working theory almost immediately, and it wasn't a dramatic one. Voyager 1 carries 3 onboard computers, each decades old, each responsible for a different set of functions. The most likely explanation, engineers agreed early on, was a fault somewhere inside one of them. Not a strike from outside, not an external event, but something failing quietly from within. The kind of internal decay that eventually comes for every machine built by human hands. Confirming that theory, however, meant solving a problem no engineer on the mission had ever faced quite like this before: diagnosing a computer that could no longer describe its own symptoms. 15 billion miles. That's roughly how far Voyager 1 sat from Earth in November 2023, a distance so vast that even a message moving at the fastest possible speed in the universe needed more than a full day round trip just to ask a question and receive an answer. 46 years. That's how long the spacecraft's core systems, including the specific component now suspected in the failure, had been operating continuously, decades before solid-state drives existed, long before anyone imagined flying a mission on hardware you could no longer buy replacement parts for because no one manufactured it anymore. 3 onboard computers. That's how many independent systems Voyager 1 has carried since launch. One of them, the attitude control system, had already caused a scare back in 2022 when it began reporting nonsensical readings about the spacecraft's own orientation. That fix turned out to be almost simple. Route the telemetry through a working computer instead of a dead one. One working antenna. That's how many ways Voyager 1 has left to talk to Earth at all. A single high-gain dish fixed to the spacecraft since before it left the launch pad, with no way to repair it, upgrade it, or replace it if it ever failed. This time would not be simple. To understand why the 2023 failure mattered so much, it helps to understand what Voyager 1 had already done to earn its place as the most consequential spacecraft in the history of American exploration. Launched on September 5, 1977 from Cape Canaveral, Voyager 1 was built for a 5-year mission. Fly past Jupiter, fly past Saturn, take its pictures, and finish. It flew past both, returning the first close images of moons and storm systems no telescope on Earth had ever resolved clearly. Then, instead of finishing, it kept going. Some of what it found along the way rewrote textbooks on the spot. Passing Jupiter in March 1979, Voyager 1's cameras caught something no one had planned to look for. Active volcanoes erupting on the Moon EO, the first confirmed volcanic activity ever observed anywhere beyond Earth. At Saturn, 18 months later, it returned the first detailed look at Titan, a moon wrapped in an atmosphere thicker than our own, hiding whatever lay on its surface behind a haze of orange smog. Neither discovery had been part of the mission's original checklist. Both reshaped how scientists thought about the outer solar system for decades afterward. None of that would have been possible without an alignment of the outer planets that happens roughly once every 176 years, a rare arrangement of Jupiter, Saturn, Uranus, and Neptune that let a single spacecraft use each planet's gravity to slingshot toward the next. Engineers in the 1960s had recognized the window and built the mission around it. Miss it, and the next opportunity wouldn't arrive until long after everyone involved was gone. In 1990, from nearly 4 billion miles away, engineers turned its camera back toward the inner solar system and captured a single pixel of light, Earth, reduced to what one scientist on the mission would later call a pale blue dot, suspended in a beam of scattered sunlight. By December 2004, Voyager 1 had crossed the termination shock, the boundary where the outward pressure of the solar wind slows below the speed of sound. By August 25, 2012, it crossed the heliopause entirely, the true edge of the sun's influence, and became the first human-made object to enter interstellar space. It still carries, bolted to its side, a gold-plated record. Sounds and images meant to describe humanity to whatever, someday, might find it. Greetings in dozens of languages, music from different centuries and continents, the sound of a human heartbeat. The record was assembled under a tight deadline in 1977, chosen by a small committee that had to decide, with almost no precedent to guide them, what a single disc could possibly say on behalf of an entire species. They settled on images of scientific formulas and everyday street scenes, recordings of thunder, wind, and whale calls, and a spoken message from the sitting President of the United States. None of it was designed to be read anytime soon. The nearest star system Voyager 1 could conceivably approach lies roughly 40,000 years in its future, still traveling, still carrying that message, long after every person who worked on the mission has been gone for centuries. That is the machine that, in November 2023, stopped making sense. For months, the standard fixes did nothing. Engineers tried resets. They tried isolating individual systems one at a time, hoping to find the point of failure. The garbled signal kept arriving, unchanged, a steady transmission with nothing readable inside it. Then, in early March 2024, the team tried something riskier, a diagnostic command nicknamed a poke, ordering Voyager 1's flight data system, the onboard computer responsible for packaging science and engineering data before transmission, to send back a complete readout of its own memory, whether or not the system could interpret that memory correctly anymore. On March 3rd, the response arrived. Most of it was still unreadable, but one section looked different from the rest of it. Structured, patterned, unlike the noise surrounding it. Every command sent to Voyager 1 and every fragment of a response it returns passes through one of 3 enormous dish antennas making up NASA's deep space network, positioned roughly 120 degrees apart around the planet in California, Spain, and Australia, so that as Earth rotates, one of them is always facing the right patch of sky. The largest of these dishes stretches 230 feet across, built to gather a signal so faint by the time it reaches Earth that its total power is measured in fractions of a billionth of a watt. Listening for Voyager 1 has never been a matter of volume. It has always been a matter of knowing exactly where and exactly when to point an enormous dish at an almost imperceptible whisper. That was the fragment the Deep Space Network engineer decoded by hand, cross-referencing it against decades-old documentation built for exactly this kind of manual decryption. What the decoded memory revealed was this. Roughly 3% of the flight data system's memory had been corrupted, traced to a single failed chip responsible for storing part of the system's own operating code. The chip wasn't malfunctioning on and off. It was frozen, a single stuck bit, locked permanently at one value, unable to store or release new information ever again. Anomaly 1. A fault with no warning and no obvious trigger, on hardware that had run without interruption for 46 years. Anomaly 2. A repair that had to happen without ever touching the spacecraft. Surgery performed across 15 billion miles of empty space, using nothing but radio commands and patience. Every step of the repair carried its own risk of making things permanently worse. A single misplaced command, sent to a computer already operating on corrupted memory, could have overwritten something essential, rather than something broken. There was no way to test the fix on a duplicate spacecraft first, no way to undo it if it failed, and no way to know for certain it had worked until the reply finally arrived, more than a full day later. Every command the team sent that spring was, in effect, a one-way bet placed against nearly 50 years of accumulated uncertainty. The fix itself demanded a kind of engineering few people on Earth are ever asked to attempt. The corrupted code needed a new home somewhere else in the flight data system's memory, but no single block of free space was large enough to hold it whole. Engineers split the surviving code into smaller pieces, found scattered room for each fragment, and then rewrote every other piece of software that had once expected to find that code sitting exactly where it used to be. A puzzle solved almost entirely by hand, since no complete blueprint of the spacecraft's original memory layout, down to the byte, still existed anywhere on Earth. On April 18, 2024, the command was transmitted. 22 and a half hours later, it reached Voyager 1. By April 20th, readable engineering data began arriving again for the first time in 5 months. In June, a second relocation of code brought the spacecraft's remaining science instruments fully back online. measurements of magnetic fields and plasma waves drifting through interstellar space, data no other operating machine in human history is positioned to collect. Voyager 1 had, in the most literal sense, remembered how to speak. Almost no one who built Voyager 1 is still working on it. The mission has passed through generations of engineers, many of them recruited specifically because they were willing to learn a programming language and a set of systems that stopped being taught in most universities decades ago. Some team members have spent entire careers on this single spacecraft. Others arrived only in the last few years, trained by the handful of veterans who still remember how the flight data system was originally wired, aware the whole time that their own knowledge will eventually need to be passed down again, to people not yet born, for a spacecraft that may still be transmitting long after that. What it went back to measuring is not small. Its plasma wave instrument listens for the faint vibrations of charged particles drifting through the space between stars, a kind of ambient hum, far too faint for human ears, that told scientists in 2013 the spacecraft had already crossed into a genuinely new region of space, months before anyone could confirm it any other way. Its magnetometer tracks the direction and strength of magnetic fields no probe had ever measured this far from the sun. Every year the spacecraft keeps functioning, that data set grows longer, and there is still no second mission, no backup probe, positioned to take over the reading if Voyager 1 ever goes silent for good. When Voyager 1 first crossed into that region in 2012, the plasma readings it sent back didn't match what several existing models had predicted. The density of charged particles out there was measurably different from what scientists had calculated in advance, forcing researchers to revise their understanding of exactly where the sun's influence ends and true interstellar space begins. It was a small correction, made possible only because a single aging spacecraft happened to be in a place no instrument had ever reached before, and happened to still be listening when it got there. In the months before the cause was known, the uncertainty didn't stay contained to engineering circles. Online, theories multiplied fast. Some speculated about undetected cosmic phenomena disrupting the signal from the outside, some kind of interstellar interference no instrument had ever measured before. A smaller, louder corner of the conversation floated something bolder. The idea of contact, that something out past the edge of the solar system had reached back and touched humanity's most isolated machine. It made for a compelling story. It was not, by any account from the people who actually solved the problem, a plausible one. The engineers who traced the fault described something closer to inevitability than mystery. A component built in the 1970s, running continuously for 46 years in conditions no manufacturer had ever tested it against, had simply worn out, or, just as plausibly, had been struck at some point by a single high-energy particle passing through interstellar space, flipping one bit permanently and silently with no witness and no warning. Nothing about the failure pointed outward, toward the unknown. Everything about it pointed inward, toward age, toward the ordinary physics of very old electronics eventually doing what very old electronics do. There was a deeper, quieter reason the failure was so hard to predict. The chips flying on Voyager 1 were never designed with the kind of radiation shielding modern spacecraft carry as standard equipment, because in 1977 nobody expected this hardware to still be operating half a century later, this far from the shelter of the sun's own magnetic field. A single stray particle arriving from anywhere in the galaxy was always going to be a possibility. It was simply never expected to matter, because nothing built in that decade was expected to still be listening for it. The Voyager team has described episodes like this one gently as simply part of operating a spacecraft this far past its expected lifespan. It had happened before, in smaller ways. It would happen again. And it did. In February 2025, engineers powered down Voyager 1's cosmic ray subsystem, one of the last of its original 10 scientific instruments, to conserve a power supply with no way of ever being replenished. The following month, its twin, Voyager 2, lost a comparable instrument for the same reason. Then, in May 2025, the mission faced its most dangerous decision yet. Voyager 1's primary thrusters, the ones responsible for keeping its antenna pointed with precision at a planet 15 billion miles away, showed signs of clogging after decades of continuous use. The only available backup was a set of roll thrusters that had sat completely dormant since 2004, untouched for more than 20 years. Firing them cold risked a small onboard explosion. Leaving them off risked something worse, losing the spacecraft's aim at Earth forever, permanently, the moment its primary system finally gave out. Engineers warmed the old thrusters slowly, carefully, testing each step before the next. Then they fired them. They worked. By April 2026, Voyager 1's power output, generated by the steady, irreversible decay of plutonium sealed inside it before launch, had fallen to less than half of what it produced the day it left Earth. On April 17th, engineers shut down another instrument, the low-energy charged particles experiment, leaving the spacecraft with only 2 of its original 10 still switched on. 4 watts. That is roughly how much electrical power Voyager 1 permanently loses every single year, with no way to ever get it back. There will come a year, not many from now, when there is no longer enough power left to keep even those last two instruments running. When that happens, Voyager 1 will not stop moving. It will not stop existing out there in the dark between the stars. It will simply stop telling anyone ever again what it sees. For now, it still speaks. Every readable signal that reaches Pasadena is a message from a machine built before the word interstellar meant anything to human engineering, proof that something launched in 1977, carrying less onboard memory than a single modern photograph, can still be coaxed back from the edge of total silence, one painstaking command at a time. Other spacecraft from the same era have already gone quiet for good. Pioneer 10 fell silent in 2003. Pioneer 11 stopped responding years before that. Both were built around the same time as Voyager 1, sent outward on similar trajectories, and both eventually reached a point where a failure could not be talked back from across such enormous distance. Voyager 1 has now outlasted both of them by decades, not because its hardware was fundamentally stronger, but because a rotating cast of engineers, most of them born long after the spacecraft launched, has kept finding one more fix, one more workaround, one more command, sent across 22 and a half hours of empty space. You need to understand what that actually means. Somewhere out past the edge of the sun's influence, a computer older than most of the people tracking it is still running code written for a mission that was only ever supposed to last 5 years. It has already lasted almost 10 times that long. It has already survived a failure that, by every reasonable estimate, should have ended its story in silence. The question facing the Voyager team now isn't whether the spacecraft will eventually go quiet. It will. Every engineer working the mission knows that. The real question is what Voyager 1 manages to tell us before that happens, and whether somewhere inside the last readable transmissions of its life, there is one more discovery still waiting in the noise, one more signal worth decoding by hand. Every one of us is, at this exact moment, roughly 15 billion miles closer to that silence than we were when this sentence began. So is Voyager 1. The difference is that it has spent nearly 5 decades finding ways to keep talking anyway, one impossible fix at a time, long after everyone who built it assumed the story would already be over. If you want to be there when that story finally gets told, stay close. This spacecraft isn't finished talking yet.